decades, the universe seemed to tell a simple story. Galaxies are drifting apart, and the expansion of space is accelerating. Scientists called this mysterious force dark energy, a term that instantly captured imagination and headlines alike. But what if everything we thought we knew about dark energy is wrong? What if the very measurements, assumptions, and models we trusted are misleading us, hiding the true nature of the cosmos? Recent research, new observations, and reanalyses of data are shaking the foundations of cosmology. The universe we thought we understood might be far stranger and far more mysterious than anyone realized. In this video, we explore how scientists might have misread dark energy, why it matters, and how our understanding of the cosmos could change forever. Body. The birth of dark energy. The story begins in the late 1990s, when astronomers observed something that would rewrite textbooks. Two independent teams were measuring distant supernovae to track the expansion of the universe, expecting the familiar pull of gravity to gradually slow cosmic growth. Instead, the results were shocking. The universe appeared to be accelerating, drifting apart faster than anyone predicted. Gravity, the force thought to govern the motion of galaxies, seemed to be defied on the grandest scale. To explain this anomaly, scientists proposed a mysterious, invisible force, dark energy. It was theorized to permeate all of space, acting as a subtle anti-gravity push that drove cosmic expansion. At first, dark energy was a convenient placeholder, a way to account for observations that didn't fit existing models. Over time, it became an accepted component of the standard model of cosmology, believed to make up roughly 68% of the universe. Yet from the very beginning, profound questions lingered. How could something so dominant remain completely invisible? Why did its properties seem almost too perfect to fit calculations, as if finely tuned for the universe we observe? Dark energy has never been directly observed. It is inferred from the motion of galaxies, the behavior of light from distant stars, and the large-scale structure of the cosmos. These indirect measurements are precise but dependent on assumptions and models, hinting that our understanding of the universe might be far from complete, and that even our most fundamental theories may require bold rethinking. Measuring the universe, the perils of assumptions. Astronomers rely on standard candles, supernovae whose brightness is thought to be known, to measure cosmic distances. The logic seems simple. If you know how bright something truly is, you can calculate how far away it must be based on how dim it appears. But what if the assumptions about these standard candles are flawed? Recent studies suggest that variations in star types, local environments, and cosmic dust may have skewed measurements. Even a small miscalculation in distance can lead to a huge misunderstanding of the universe's expansion rate. Then there's the matter of the Hubble constant, the number that describes how fast the universe is expanding. Two methods of measurement, one using nearby galaxies, another using the cosmic microwave background, consistently give different results. This discrepancy, known as the Hubble tension, is one of the biggest unsolved problems in cosmology. It hints that our understanding of dark energy, or even the fundamental laws of physics, could be flawed. The Standard Model and its limits. The Standard Model of cosmology assumes a universe dominated by dark energy, dark matter, and ordinary matter, following equations derived from Einstein's general relativity. But models are only as good as their assumptions. They simplify reality to make calculations possible. If a foundational assumption is off, even slightly, the conclusions drawn from it can be misleading. For example, the universe might not require a mysterious dark energy at all. Some theories suggest that modifications to gravity at cosmic scales could explain the acceleration, removing the need for an invisible force entirely. Others propose that inhomogeneities in matter distribution, clusters and voids of galaxies, might create the illusion of accelerated expansion. In other words, what scientists interpreted as dark energy could be a symptom of misreading the universe, rather than a fundamental cosmic ingredient. New observations, new mysteries. In recent years, instruments like the James Webb Space Telescope, advanced galaxy surveys, and high-precision cosmic microwave background studies have begun to provide details of the universe with unprecedented accuracy. Astronomers can now observe farther, see fainter light, and measure cosmic phenomena more precisely than ever before. Some of these new observations directly challenge long-held assumptions. For example, supernovae, the so-called standard candles, appear slightly different in brightness and behavior than models predicted. The rate of cosmic expansion seems to vary depending on direction and location in space, while the large-scale structures of galaxies and voids are far more intricate and uneven than previously imagined. These discrepancies suggest that either our measurements or our underlying theoretical frameworks may be incomplete. Each unexpected finding forces scientists to re-evaluate the very foundations of dark energy, considering whether it is a true cosmic force or a misinterpretation of complex, nuanced data. Science thrives on questioning assumptions, and in the case of dark energy, these questions are becoming increasingly urgent and impossible to ignore. Implications for cosmology. If dark energy is not what we thought, the consequences for cosmology are staggering. The universe might not be on a path toward a cold, empty, ever-accelerating expansion as previously believed. Galaxies, stars, and even the large-scale structure of the cosmos could evolve in ways that fundamentally challenge our models. Our understanding of physics itself may need revision. Concepts such as gravity, space-time, and energy might behave differently at cosmic scales than current theory predicts. Even the cosmic timeline, the age of the universe, and the history of galaxy formation may need recalculation. Every simulation, every measurement, and every theoretical model that incorporated dark energy would require re-examination. This is far more than speculation. It represents a potential scientific paradigm shift comparable to the revolutions that placed the Sun at the center of our solar system or revealed the universe's expansion. Such a shift could redefine our place in the cosmos, altering not only scientific understanding, but humanity's sense of the universe itself. Why scientists might have gotten it wrong. Science is an extraordinary tool, but it is not infallible. Even decades of meticulous research can lead to conclusions that later require major revision. In the case of dark energy, multiple factors may have contributed to scientists potentially misinterpreting the data. Observational tools, while advanced, are still limited by precision, calibration, and cosmic interference. Small measurement, errors, or overlooked environmental effects can cascade into significant miscalculations at the scale of the universe. Furthermore, scientific models are simplifications of reality built on assumptions that help make complex systems understandable but can unintentionally obscure key variables. Peer consensus, while essential for scientific validation, can sometimes reinforce prevailing theories before alternative explanations are fully explored. The universe itself is vast, subtle, and often counterintuitive, reminding us that even the brightest minds can be misled by appearances. Recognizing these limits is not a failure. It is the essence of scientific progress, pushing humanity to refine tools, question assumptions, and explore deeper truths. The road ahead, the next decade, promises to be revolutionary. Telescopes and space missions will probe the universe in unprecedented detail, mapping galaxies, measuring cosmic expansion, and testing the limits of gravity. Alternative theories will be scrutinized. Simulations will incorporate more variables. Cosmologists will explore whether dark energy is real or a cosmic mirage created by assumptions and observational limits. The process is painstaking, meticulous, and thrilling. Each discovery brings both clarity and new mystery, keeping the quest to understand the universe alive and dynamic. Outro. Dark energy may not be the force we imagined. The universe is more complex, surprising, and enigmatic than we ever dreamed. Science does not always get it right the first time, and that is its strength. Each correction, each new observation, brings us closer to the true nature of reality. As we continue to explore, question, and observe, we are reminded that the cosmos is not static. It is alive, mysterious, and constantly challenging human understanding. For anyone captivated by the universe, these revelations are not just scientific, they are cosmic. Storytelling at its finest. If you're fascinated by the mysteries of the universe, subscribe for more cosmic explorations. Like the video if it blew your mind, and share it with fellow stargazers and science lovers. Comment below, what do you think dark energy really is? Your idea might inspire the next big question in astronomy.